Welcome to this video lecture. My name is Mark Scythian. The date today is October 18th, 2021. The title of this lecture is Hydraulics, Pneumatics, and Pascal's Law. This lecture will focus on illustrating the concepts supporting pneumatics and hydraulics under the concept of Pascal's hydraulic lever. In this case, we're going to work with a pneumatic-powered hydraulic press, also under the application of pneudraulics, a combination of pneumatics with hydraulics. So here, the function is to amplify force through the hydraulic lever, for which Pascal's law asserts that when a fluid, either a liquid or a gas, is transmitting pressure and then subsequent force, the pressure across the fluid medium, in this case incompressible liquid, known as hydraulic fluid, will remain constant throughout the incompressible liquid medium. So we know that force is equal to pressure times area, especially upon an enclosed surface like a piston circular area, times the applied pressure in pounds per square inch or pascals. So here the hydraulic lever is amplifying a force input into a greater force output at the expense of displacement. So here we'll start with the air compressor. It's rated at 180 psi gauge pressure. It then transmits 120 into a compressed air accumulator. We then have some sort of a graduated discharge valve to release the 120 pounds per square inch of compressed air pressure inside of a smaller cylinder in relationship to a larger cylinder and larger piston. So we have a smaller piston, a master cylinder, which contains a piston, and on the input side is a compressed air zone, and on the other side is an incompressible fluid, in this case a liquid in the form of hydraulic fluid, with all of the air and gas bled out. So when pressure is transmitted upon this liquid fluid, which is not compressible, it behaves as an amorphous solid. A solid but taking the shape of the container or cylinder. So by this means, we can apply the 120 pounds per square inch gauge pressure compressed air upon the piston head area. So in this case, the piston is 8-inch diameter, pi r squared, the diameter divided by 2 radius, radius squared times pi. We then yield 50.3 square inches of piston head surface area at the small piston, blue piston here. So that means for every 1 psi g applied to this piston, there will be 50.3 pounds force transmitted by the piston. So we're going to apply 120 psi as just a cycle test to see the maximum limitations of the device. So in that case, we compute 120 psi g times 50.3 square inches to yield 6,036 pounds force transmitted by the small piston in blue, remembering that the pressure transmitted across the liquid incompressible fluid or the hydraulic fluid is constant. So that means also 120 psi g gauge pressure is transmitted across the large piston, which has a 24-inch diameter. So half of its diameter is the radius squared times pi. That's a typo there. That squared should be here. So 24 divided by 2 squared times pi, 452.4 square inches of cross-sectional area at the large green piston here. So 120 psig times 452.4 will yield 52,288 pounds force output at the large piston. However, the compensation is the displacement. Notice that at 33 inches of small piston displacement, the force will amplify from 6,036 pounds force to 52,288 pounds force at the expense of displacement of the piston. So 33 inches of travel here, 6,036 pounds of force will yield 3.81 inches of large piston travel with 52,288 pounds force output. So this is an example of Pascal's hydraulic lever. Just like a lever has mechanical advantage, the farther away the lever force is making from the plane of rotation as a radius, the mechanical advantage increases. So the displacement will decrease. So this is a very excellent, efficient device to apply force incrementally or continuously by amplifying force. So we see this with hydraulic jacks, hydraulic hoists in automotive garages, and the practical application is to apply compressed air pressure instead of something manual, so that some sort of a graduated valve or even a pumping valve with a check valve can assist the process of applying force to the input cylinder and conveniently result in output force at the large piston. So this could also be connected to a sensor, and position sensing on the application can then trigger the prescribed air pressure charge in order to induce the input force required for some predetermined force amplification output. So moving on here, we will use a specifications to put this device into good use. For example, in this application, we will be pressing a bearing into a bearing race as part of automation assembly processes. So the specifications as calculated in the assembly design require 48,000 pounds of force to press the bearing into the bearing race. The entire large piston actuator and press assembly in green have a weight of 750 pounds. And because they're going vertically, we're going to reassign the pounds mass into pounds force in the form of force weight. So the overall amplification of force output at the green piston, the large piston, is determined as 48,750 pounds force. Okay, so we need to actuate this press 1.905 inches, which is the distance the bearing must move in order to insert into the bearing race to complete the duty cycle on the assembly. But this displacement must occur over a 5-second time period, not less and not more. This has been predetermined based on the assembly design. So this is a relatively high amount of force, a low amount of velocity in order to properly insert the bearing without damage. This is an interference fit, and based on the hardness of the material and the interference oversizing, this piston the large piston will have to move at that exact velocity, or 1.905 inches over a time period of 5 seconds. Okay, so now the application has been defined, and we can move on to no load calculations with proof, followed by no load metrics. So after determining the force outputs, we can establish the displacement ratio by taking the ratios of the force. So if we're going on the low end of displacement, the output cylinder, 6,036 divided into 52,288. The other way around, 52,288 into 6,036 would yield 8.66. So the small piston will travel 8.66 times greater than the small piston will travel 8.66 times more than the large piston. And the return is an increase or an amplification of force. But we are not changing the overall power and energy in the system, because the system's net power input and output come to zero, as observing the first law of thermodynamics. So we have key points, constant pressure, force in this case, based on Pascal or Bernoulli force, is pressure times piston cross-sectional area. Inversely proportional piston displacement over the function of force. Small piston is equal to greater displacement. Large piston is equal to less displacement, and force amplified at large piston. So we next have to prove if these calculations are correct. So we will compute the overall work completed by the small piston and the large piston, work being force times distance. So we take the force times the distance traveled in feet, 16,600 foot-pounds at the small piston, and then the force output at the large piston times its displacement, also 16,600 foot-pounds. Proof correct. Okay, so now we have the right information to proceed on with the no load metrics. Small piston input displacement 33. This is the maximum cycle operation maximum. So a large piston output 33.81. We have a constant pressure of both pistons, small and large, and then we have, of course, the force output, the force input and output of the piston. So we have the specifications listed for the application defined, and then we have a summation force of 48,750. So all we have left to compute is the actual force it takes to move a 10-pound small piston. Of course, the 10-pound small piston weighs 10 pounds right there, and that's after we have applied the correct pressure at the small piston to negotiate the 48,750 pounds force. So it's an extremely minute amount of pressure to actually displace the F is equal to ma force component. So that's the Newtonian force. It's very minuscule, if any. It's all Pascal and Bernoulli force, or pressure times area. So moving on here, we go over to the load calculations. So the small piston to large piston displacement ratio, as previously mentioned, 8.66 to 1. We have a large piston velocity of 1.905 inches per 12 feet. That's feet over 5 seconds, so 0.03175 feet per second. And because the displacement is inversely proportional, we also can compute the velocity at the small piston. So that's none other than the velocity at the large piston times 8.66, so 0.275 feet per second at the small piston. And then the small piston displacement, in this case, it limits 16.5 inches at the small piston and 1.095 inches at the large piston. So next we have to move on and calculate the small piston acceleration. So we know distance divided by time squared is acceleration. So we can then compute the distance in feet, so 16.5 inches into 12 feet 12 inches per foot, so that's 16.5 feet divided into 5 squared, so 0.055 feet per second squared. Small piston acceleration, and then of course again the displacement distance at the large piston in feet divided into time squared, 0.00635 feet per second squared. Small piston mass, 10 pounds. Now we're dealing with mass, not force. Force is mass times acceleration. So we can use the metric system for clarity and ease of simplification. And 10 pounds converted into kilograms, so 4.54 kilograms. So the force to overcome small piston mass accelerated to 0.055 feet per second squared is the mass of the piston times its acceleration, and the small piston that is, so 0.25 newtons, very small. There's 4.45 newtons to 1 pound of force, so it's a very tiny amount of force, 0.06 pounds at the small piston. So now we can go back to Pascal and Bernoulli force, which is pressure times area, air pressure times piston cross-sectional area. Required air pressure at small piston to transmit 48,750 pounds force to large piston is equal to the 48,750 pounds force divided into 8.66, and then that determines the force at the small piston, then divided, remember pressure is force divided by area, so divided into the cross-sectional area of the small piston, which is 50.3 square inches, so 111.92 psi is what we'll need, and then the required air pressure to overcome the coefficient of kinetic friction at the small piston, which is also a function of its mass, 4.54 kilograms, 10 pounds mass, not force, is very, very tiny, so it's going to be 0.06 pounds force divided into the small piston cross-sectional area. So there you go, it's very minuscule. And so that's within a tolerance, and it's greater or less than on the instantaneous force. You can prescribe a round-up tolerance. It's not going to really affect the minuscule approaching zero force to move the small piston. But it is something that should not be neglected. Sometimes it is. Sometimes small pistons can weigh substantially high, so it is a good habit to also compute the Newtonian force component. So in this case, it's approaching zero, but we will add it anyway. So it's more or less 112 psig, but the exact specificity is 111.92. So the calibrations on the graduated discharge valve here can be set to a ramp up 112.0 psig, thus delivering that overall pressure charge over the prescribed time and displacement limits, and then you accomplish exactly what was designed, a 1.905 inch travel over 5 seconds, transmitting 48,000 pounds of force to press the bearing in, and then the 750 pounds force to actuate the large piston assembly, which includes the actuator and hydraulic press, leaving out the 48,000 to transmit into the bearing, successfully pressing it into the bearing race. So you see the deductive reasoning taking place, and we have an equilibrium for the given function. So moving on, the last part of this lecture is many times the cycle power and life cycle analysis will be something of consideration, especially on the manufacturing engineering sense. So the required pneumatic or compressed air power should be calculated. So we have the force output divided into the displacement ratio at the small piston plus the minuscule force to overcome the Newtonian force component times the speed of the small piston during the cycle times the 5 seconds. So we have the work, the force times distance, thus quantified. So we have a force times your distance. So we take the velocity times time to get distance. Then we have the force at the small piston, which is the force at the large piston divided into the displacement ratio plus the minuscule force, Newtonian force, to move the piston to overcome its kinetic friction or coefficient of kinetic friction. And so that establishes the force component times the distance component, the velocity 0.275 feet per second times the time. So now the seconds cancel out, you're left with distance. And so that's the work component. But then when we take force times distance or work and we divide it into the time, then we get power. So work divided by time is power. And then work itself is the foot-pounds, and power is the foot-pounds per second. So this computes 1548.1 foot-pounds per second power, pneumatic power during the 5-second cycle, but that's per second. That is the duty cycles, time duty cycles 5 seconds, but it's a 1548.1 foot-pound per second cycle power at the pneumatic load. And then so we compute that then into wattage. We know that 0.737 foot-pounds per second is equal to 1 watt. So when we multiply the foot-pounds per second mechanical power times the conversion factor of foot-pounds per second to watts, we get 1141 watts. And then most air compressors, reciprocating air compressors, are going to operate at a 60% efficiency, which means 60% of the input power, in this case electrical power, to run the compressor is converted into compressed air power potential or pneumatic power potential. So it is still a potential energy in the tank, but when it's released over all the different duty cycles till it's recharged and the air compressor is recharged, the overall cycle efficiency on the air compressor industry standard is about 60%. So we could take the reciprocal of 1 over 0.6 or 60%, multiply that times the pneumatic power to yield 1902 watts of electrical power, in this case AC electrical true power. And so if we wanted to know the kilowatt hour consumption during the cycle load, we could simply take the 1902 watts and multiply it times the number of hours the electrical power is running. So each cycle is 5 over 3600, which is the number of seconds to an hour. So 5 over 3600 times 1902 watts yields 2.64 kilowatt hours per bearing insertion cycle. So that gives you an idea of the power distribution, the power consumption, and then ultimately the mechanical efficiency involved, which then allows further specs to be written on the life cycle analysis. So this is all very important because then any modifications or changes to the components, the cross-sectional area, the diameter, when and where the compressed air will charge, usually a pocket zone can accumulate enough load so the velocity, acceleration, and distance graduation are stabilized. So it's a sufficient volume to accumulate compressed air, and then you transmit that force through the amorphous solid, the incompressible liquid, the hydraulic fluid, bled of all gases such as air out. And then above the actuator, large piston, you have air, and then a panel, and then there's vents here. So you have good ventilation. And then when you drop the air charge through the graduated discharge valve, has the relief valve on the closed side, open side, closed side. You then have metering valve that discharges the compressed air somewhere else or back into a refill zone that has the air filtration. It could go back into the atmosphere or into an accumulator, secondary accumulator, and then the weight and the lack of pressure at the small piston then graduates the hydraulic press to come down in a smooth and controlled manner. So that's all in the relief valve, shuttle valve, and metering pins. It's all in the graduated valves. So that's the other side of hydraulics is the relay, sequence, and shuttle valves, which is predetermined if you need them. But many more hydraulic and pneumatic circuits have those accommodated in the entire valve circuitry, the pneumatic and hydraulic valve circuitry. So that could be metering pins, that could be the relief valves, that could be the check valves. So that's all part of an industrial standard. So we've got a pretty good, overall, we have a pretty reasonable efficiency from the amount of force and the amount of value put into such a bearing. We're not spending much time on the cycles, and we're getting a consistent press pattern at near effortlessly on the charge, and we don't have necessarily the wear and tear. We have a pre-lubricated bore on the air side and rings, and then we have a graduated hydraulic incompressibility. So then that leads to the last inquiry is the thermal induction and hydraulic compressibility. And it's something like this, unlike, let's say, hydraulic braking systems where you have to induce heat and friction. You have to induce heat to get the friction, and then you have to dissipate the heat. So you're dealing with a completely different thermal induction and hydraulic compressibility, mainly a change out on the DOT3 hydraulic fluid, the brake fluid, and the bleeding process. But the thermal induction, that's something significant in automotive braking systems. And we have more of the phenolic pistons and the transfer of heat distributed through, say, the metallic rotors, and then they have somewhat impellers on the cooling side within the double stacked impeller rotor designs. So that really cools the system quickly. But that is another inquiry on life cycle analysis, is what kind of thermal loading is going to build up. But we're not dealing with sudden hydraulic inputs, outputs like with automotive braking, and we are also graduating the force and pressure distribution across the fluid. So then that means we have negligible thermal induction, which is something to consider because you're going to run into, in your thermodynamics work, in your thermodynamics modeling, you're going to run into pneudraulic systems. And some of them are designed to actually have condensers to accumulate that energy into other systems, the thermal energy, instead of wasting it. So this is not really applicable because we're dealing more of a high amount of force, low amount of displacement application. So, but that is a consideration. On other pneumatic or hydraulic applications, the thermal induction is a significance, and there is a slight amount of hydraulic compressibility, like 0.3%, something like that. And you have to accommodate that, especially if there's changing temperatures and the possibility of vaporization and even condensation of seals are compromised. So that has to be a consideration. So I did list the thermal induction, and some of your hydraulics, pneumatics, thermodynamics, fluid mechanics homework is going to run into this whole thermal transfer and thermal distribution, heat exchanger sometimes, especially expansion valves, and you may be dealing with condensers that are dealing with hydrostatic systems like torque converters. So this is actually outside of that scope because it's not dealing with, it is a dynamic system, of course, but the instantaneous dynamics is not as aggressive here. So that's been addressed. And so now we have pretty good, sufficient specifications to then describe many other applications if need be. So we can write the final specs here as listed. These are in both the US imperial units and also the metric system. And so you can write the final specs here, and you have a good idea of the methods and acceptable practices in modeling low dynamic hydraulic and pneumatic systems in accordance to Pascal's law Pascal's triangle and the mathematics behind it, and of course the power function. It's all very brilliant. So keep an eye on Pascal's law for many other applications in physics. Thank you for watching this lecture and have a great day.